Hello everyone. This video is recording my assignment for Programming Language Translator course, which is a part of my B.Tech curriculum in V.I.T University. So let's get started. Let me introduce myself. I am Harish Kandala and my registration number in V.I.T University is 13 BCE 0164, and this assignment is for course CSE 309, which is also called as PLT or Programming Language Translators of slot C1, and I am doing this assignment under faculty Professor Kannadasan R. I would like to specially thank Professor Kannadasan who gave us an opportunity to do this assignment and also who guided and encouraged us all through the semester. This assignment totally has 3 problems, and the first one is, with the help of neat block diagram, explain various phases of compiler. Also write down the output of each phase for expression a equal to b plus c into 15. So in this problem, I am going to describe each and every phase of the compiler using this example expression a equal to b plus c into 50. And the second problem is, consider the following CFG. E gives tr, r gives plus tr, r gives minus tr, r gives epsilon, t gives num, with the translation scheme to generate postfix expression equivalent to the given infix expression, which is recognized by the above grammar. All action is in the translation should be at the end of each production. So in this problem, they gave us one CFG, and this CFG represents the all infix expressions only including plus and minus signs, not any other signs. So using this infix expression, we have to find out or generate the semantics, or which is also called as actions, which should be only at the end of the productions, and using that actions we need to generate postfix expressions. And the third problem, and in the third problem is, what is L attribute definition? Support your answer with example. So we already know there are two types of attributes, which is called S attribute SDT and L attribute SDT. In this problem, I am going to explain what is S attribute SDT and what is L attribute SDT, and we'll compare the differences, and we'll also take an example of L attribute and understand its meaning. So let's get started by one. Problem 1. So as we know, the problem 1 is, with the help of neat block diagram, explain various phases of compiler. Also write down the output of each phase for the expression a equal to b plus c into 50. The compilation process is a sequence of various phases. Each phase takes input from its previous stage, has its own representation of the source program, and feed its output to the next phase of the compiler. Let us understand the phases of compiler. So basically, there are 6 phases of compiler. First one is lexical analysis, syntax analysis, semantic analysis, intermediate code generation, and finally the code optimization. Let's go through them one by one. So the first stage is lexical analysis. In this lexical analysis stage, this is the first phase of the scanner, which also works as text scanner. In this phase, scans the source code as a stream of characters and converts them into some meaningful lexemes. Lexical analyzer represents these lexemes in the form of tokens. So for every symbol it got in this phase, it converts them into some meaning tokens and stores them separately in some symbol table. So basically all the text or all the each and every word in the source code will be converted into some form of symbols, and all these symbols will be stored separately in some symbol tables. That's what this first stage will do. And the second stage, syntax analysis. In this stage, this is also called as parsing. in this stage, the syntax analysis or parsing. It takes the token produced. In the first stage, we produce the tokens, and these all the tokens produced by the lexical analysis as input, and this stage generates a parse tree, which is also called as syntax tree. In this phase, all the token arrangements are checked against the source code grammar. That is, the parser checks if the expression made by the tokens is syntactically correct or not. So basically, in the lexical analysis stage, we get all the tokens, but we don't know whether they are meaningful or whether they are syntactically correct or not. So in this syntax analysis stage, we generate a parse tree according to the rules which are already defined by the compiler, and we check them against these symbols and whether they are syntactically correct or not. And the third stage is semantic analysis. In the semantic analysis, we check whether the parse tree constructed follows the rules of language or not. For example, assignment of values is between compatible data types. So, integer, character, boolean, whatever. And adding string to an integer is obviously like the data types are wrong, and compiler rejects them. How it rejects? In this stage, we reject the types and all. Also, the semantic analyzer keeps track of identifiers, which are the identifiers, their types, and expressions also. Whether identifiers are declared or not, before used or not, etc. kind of things. All these things are taken care by the semantic analysis stage. And the semantic analyzer produces an annotated syntax tree as an output. So basically, semantic analyzer checks whether this it is semantically correct, like all the rules are following or not, and whether all the types are perfect, and checks whether the variable is already defined, whether the identifiers are already defined, and it's just like a go through like all the checks of all the parts tree and generates another tree which is also called as annotated syntax tree as an output of this stage. And the fourth stage is intermediate code generation. After semantic analysis, the compiler generates an intermediate code of the source code of the target mission. So, from after the semantic analysis stage, we'll get some annotated syntax tree. With this annotated syntax tree, we generate some intermediate code, which is not the exact source code, but it is the in between. We call it as intermediate code. It represents a program for some abstract mission. It is in between high level language and the machine level language. So it is not machine level language, it is not high level language, but it is somewhere in between. That is why we call it as an intermediate code. This intermediate code should be generated in such a way that it makes it easier to be translated into the target machine code. That's what this intermediate code generation does. So basically it generates some intermediate code using this annotated syntax tree. And the next stage, code optimization. We get some intermediate code in this intermediate code generation stage, but we don't know whether this code is optimized or whether it is efficient or not. This stage is for that. We optimize this intermediate code. Optimization can be assumed as something that removes unnecessary code lines and arranges the sequence of statements in order to speed up the program execution without wasting resources. So basically, we go through the intermediate code again and we check whether the code is perfectly optimized or whether there is redundant lines, whether there are unnecessary code lines, and we remove all those things and optimize the intermediate code. And the final stage, code generation. In this phase, the code generator takes this optimized representation of the intermediate code and maps it into the target machine language. Now, when we say target machine language, we mean like assembly, like that. So basically, this target machine language is dependent on the machine, whether we use 8086 or which processor we use. So the code generator translates the intermediate code into sequence of relocatable machine code. Sequence of instructions of machine code performs the task as an intermediate code would do. and all this in machine code is used to finally execute the source code in the CPU. So that's how the whole compilation process takes place. And I mentioned somewhere in this lexical analysis stage something called symbol table. So in symbol table, it is basically we store this lexical, all the symbols generated by the lexical analysis in like a hash map. So what is symbol table? The symbol table, it is a data structure maintained throughout all the phases of compiler, not just lexical analysis. We use this symbol table everywhere, like in every stage. All the identifiers name along with their types are stored here. The symbol table makes it easier for the compiler to quickly search the identifier record and retrieve it. The symbol table is also used for scope management also. So that is the main purpose of symbol table. So from this block diagram, we can visualize what exactly is going on. So basically, the source code enters the lexical analyzer, and it separates all the symbols and stores them in separately symbol table, and it goes through syntax analyzer, and you can see all the symbol table management and error detection handling or mapped to each and every stage. So, and this after the syntax analyzer, we generate a parse tree, and after this stage, we go through semantic analyzer, and we'll get annotated syntax tree. And this lexical analyzer, syntax analyzer, and semantic analyzer together can be called as analysis phase. So basically we are doing just analysis. We are not generating any code there. That's why we call it an analysis phase. And after getting this annotated syntax tree from the semantic analyzer, it will go through the intermediate code generator, which generates the intermediate code, and this code will be optimized by the code optimizer, and finally we get the final source code or machine language code from the code generator. This is the target machine code. So these are the basic, all the 6 phases of the compiler. So from source program to target machine code. So if in the question they also gave us some expression which is called which is a equal to b plus c into 50. So let's see what will be the values of this expression at each and every phase. So in the first phase, as we know, the lexical analyzer will generate symbols, like stores them in a separate names and like in a symbol table. So here a equal to b plus c, and for each symbol we are storing them as a separate name, like in a symbol table. So something called as id1, id2 and id3. So a is id1, b is id2, c is id3. These maps will be stored in the symbol table, so they can be retrieved finally at the last stage. So after lexical analyzer, the expression will be id1 equal to id2 plus id3 id1 equal to id2 plus id3 into 50. And then next it goes through syntax analyzer. Syntax analyzer generates parse tree, as you can see. So basically we are constructing the parse tree from the using the same expression. And the semantic analyzer, we are checking the types, especially here we are converting it to float. The 50 is converted into float there, so we are checking whether the value 50 is matching with the type of the float or not. And after going through, we got this annotated syntax tree from the semantic analyzer, and we got the intermediate code generated using this annotated syntax tree. So the intermediate code will be t1 equal to into float of 50, t2 equal to id3 plus t1, t3 equal to id2 plus t2, id1 equal to t3. So this is the intermediate code, and we can observe there are so many redundancy in the intermediate code, so we can optimize the code, and that is what code optimizer does. Now the code optimizer optimizes the code, and the optimized code is t1 equal to id3 plus 50, id1 equal to id2 plus t1. We basically we merge the two steps over there, and finally we got this optimized code, but we need to generate the respective machine language code. That's what code generator does, and this code generator generates the final machine language code, as you can see. So this is the solution for the problem 1. Let's go to problem 2. So the problem 2 is, they consider the following CFG: E gives TR, R gives plus TR, R gives minus TR, R gives epsilon, T gives num, with the translation scheme to generate postfix expression equivalent to the given infix expression, which is recognized by the above grammar. All action in translation should be at the end of each production. So basically we should get to know what is infix expression and what is postfix infix notation and postfix notation. So what is infix notation? Infix notation is the notation that is commonly used in arithmetic and logical formulae. That is, this is a basic notation we use everywhere, like a plus b or b plus c, b into c. The operator will come in between the operands. That is what infix notation is. Now, what is postfix notation? This postfix notation is also called as reverse Polish notation. It is a mathematical notation, like all the operators follow after operands. In infix notation, operators come in between, and in postfix notation, the operators will come after the operands. So that's the thing. That's the main difference between infix notation and postfix notation. And in the given CFG, we can observe that given CFG can represent any infix expression with only plus and minus operators. So the given question is, we need to generate actions or semantic rules using this CFG, and we need to write the actions for the particular CFG, and then such that we can generate postfix notation for the respective infix notation. So basically, we need to write the action such that we will get the postfix expression from the given infix expression. So let's go on. So the given is a simple translation scheme for mapping this infix expression and to the corresponding postfix expression. So what we does is, basically we are modifying only 3 production rules. That is, r gives plus t, r gives minus t, and t gives num. In the r gives plus t, we wrote an action in the between r gives plus t between. The action is print plus and then again followed by the r1, and r gives minus t followed by an action print minus and again followed by r1, and the last production t gives num, and we are following by a action print num dot val. Here val is a property which will be the representing the value, like 2 or 3, whatever number. So we got this translation scheme, and now let's check whether it properly works or not. Let's take an example. For suppose 5 minus 2 plus 7. So basically now we'll construct a parse tree and check whether it is printing the respective postfix expression or not. So as you can see, this is a parse tree, the constructor, and from the parse tree we'll go from top to down and to left to right, such that we'll go through like that. So the first action will be print 5, and followed by that, and we'll get the next action will be print 2, and the next will be print minus, and print 7. The last one will be print plus. So the final expression that is printed is 5, 2 minus 7 plus. As you can see, that is the exact postfix expression for the infix 5 minus 2 plus 7. So it's satisfied. That is a solution for the problem 2. Let's go to the last problem 3. So this problem is, what is L attribute definition? Support your answer with example. To understand what is L attribute definition, let's understand what is synthesized attribute. So basically there are 2 types of attributes. One is synthesized attribute and inherited attributes. So the synthesized attributes are, these attributes get value from the attribute values of the child nodes, only from the child nodes. Let's consider a production S gives ABC. So if S is taking values from its child nodes A, B, C, so if the attributes of the S takes only from the values of its child nodes, then it is said to be a synthesized attribute. And inherited attributes. In the inherited attribute this is in contrast to synthesized attribute. Inherited attributes can take values from parent and or siblings. Let's consider again the same production S gives ABC. In that production, if it is an inherited attribute, A can get values from S, B, and also C. Similarly, B can take values from S, A, and C, that is parent or any of its siblings. Likewise, C can also take values from S, A, and B. So basically, inherited attributes can take attribute values from either parent or its siblings. Now, let's get to know what is S attributed STT. So basically, we know what is an STT. STT is syntax directed translation. If an STT uses only synthesized attribute, as we can got to know what is synthesized attribute is, if an STT uses only synthesized attributes, it is called an S attributed STT. Now, the main answer to the question, what is L attributed SDT? This form of SDT uses both synthesized and inherited attributes with restriction of not taking values from the right siblings. So in inherited attribute, you can take from any sibling, either right or left. So basically L attributed SDT restricts that. We can L attributed SDT can have synthesized attribute, and also it can have inherited attributes, but restricting them you can take only values from the right siblings. So again, consider the same production S gives ABC. In that S gives ABC, if it is an L attributed SDT, S can take value from A, B and C. That is simply synthesized one. A can take values from S only. B can take values from S and C, S and A. So that is only right one. C can get values from S, A and S, A and B. No non-terminal can get it values from sibling to its right. So that is the main definition for L attributed SDT. Attributes in L attributed SDTs are evaluated by depth first and left to right parsing manner. We can also conclude that if a definition is S attributed, then it is also L attributed, as L attributed definitions encloses the S attributed definitions. So let's take an example of L attributed SDT and see whether it satisfies or not. So the given example is E gives TA, and A gives plus TA1, A gives E, T gives parentheses E and closed parentheses, T gives digit, and each have its action. Here A dot I is an attribute. It's taking its value from T, only T, yeah, that is right sibling. So yeah, it's satisfied. E dot value is taking it attribute from A, that is it's taking it from its child, that is synthesized one. So it is also satisfied. Now in the second production, A1 dot I equal to A dot I. A1 and A are basically the same thing. So as we need to differentiate both of them, we are representing them differently. So A1 dot I is taking its value from A dot I, that is it's taking from the right one. So that is also satisfied. It is an inherited attribute, and plus F dot value also, which is also satisfied. A dot S equal to A1 dot S, which is the child one, which is also satisfied. A dot S equal to the third production is A gives E, and the action is A dot S equal to A dot I, which is also satisfied, that is child one. T dot value equal to E dot value for the fourth production. Well, that is T dot value is taking its value from the child, which is satisfied, and T dot value equal to digit dot lex value for the last production. T dot value is again the same thing, it is synthesized one and taking. So all the productions satisfy are either in synthesized attribute or inherited attributes, that is restricting them only taking from the right siblings. So it is all the production satisfies those. So you can conclude this example is an L attributed SDT. So we solved all the three problems as we mentioned before. So I would like to conclude the video now. Thank you for watching.